oxygen is a triplet molecule. No? And why triplet? The two unpaired electron and the antibonding orbital, like pi star orbital, and they are not anti-parallel, they are parallel. You can make them anti-parallel, but then you have to apply some energy over there. So energetically uphill process. So the oxygen what we have in the atmosphere, that is triplet, but it can be made singlet under certain circumstances. But the spin wise, okay, if you react the triplet oxygen with one of the NO radicals, this is a radical over here, and then what happens that when they come closer to each other, then they cannot distinguish which one is up and which one is down. Some kind of spin exchange takes place because energetically, which is rather allowed situation. That means the energy which is available in the atmosphere, okay, there's the KT energy what you talk about. Huh? That amount of energy is quite good to allow the spin exchange process. And as a result, you will be seeing that two down would become one up, one down, and this will become up to, it doesn't matter for this NO. Initially it was up, now it is down, which could be measured by certain other experiments, but it doesn't matter to this molecule, but it matters a lot to this molecule. Now you are getting triplet to singlet. Okay, and this singlet now could interact to a molecule which is closed cell. Now oxygen normally, not normally, oxygen, since it is triplet, it reacts with a molecule having unpaired spin. It cannot react with a singlet molecule. Singlet means closed cell, where all the electrons are paired up. But if you have a singlet oxygen, okay, singlet oxygen generator is there. Without that, if you can make a singlet oxygen during the course of the reaction through exchange mechanism, then that singlet oxygen can also react with a closed cell molecule. So through EPR one could judge it, because once you move from here to here, you look at the three spin situation. So one, this is triplet, it has its own EPR profile, this is singlet, and at the center point you have a triplet situation. Down, down, up, whether they will couple or not, that's a separate issue. But normal circumstances, you can also think about the triplet situation or your doublet situation. But eventually what you are getting, this is it becomes S equal to 0, and you would be ended up with the doublet situation only. So you are moving from triplet to doublet. So EPR could be followed this sequence of the reactions. Now let us move to the metal complexes. So radical is normally easy to follow, but not necessarily always it is so easy to follow. There are complications, but that complications could be handled if we have the pre-understanding, pre-knowledge, and also if we understand the chemistry of that molecule. Okay, because resonance, when it comes into the picture, our mind needs to function in that direction, that what kind of resonating configuration one could conceive as far as that molecule is concerned. So many things you have to consider together, and then you will have a better perceptions or understanding through the EPR or ESR experiments of that radical system. But remember, the radicals what I have talked about so far, which is only doublet situation. That means one unpaired electron is there. Now, there are organic molecules, as I have given you an example in the I think first class. You could think about this molecule. Okay, this is a triplet molecule. Okay, though very unstable, but the EPR could tell you, yes, this is the right situation. One could reach through EPR only. One could tell. No other experiment could help you to understand it, that you are here, because you have two unpaired electron. That means S equal to 1. That is a triplet situation, and its spectral profile would be completely different than any of the items what you have over here, all single electron. But this will be actually resonating from no unpaired electron. So this form or this form would be completely different with respect to this form. So again, you can have an organic molecule the 3 unpaired electron up instead of down one. Okay, 3 up. Now, if you have a 3 up situation, that will be extraordinarily complex situation. So, well, we should not be afraid of the complex situation. We should only try to understand how to handle the complex situations, right? Okay, but as far as the organic is concerned, which is in general, it is not that difficult, but there are occasions where one needs to also handle the complex situation. For example, I said the triplet situation, which is rather difficult. Now, once you go to the metal system, I'm talking about metal complexes, basic principles are same, because you see that's like radical. If you have one unpaired electron, you can think about minus up, plus up, and then that would be splitted based on the hyperfine or super hyperfine. Now you need to always remember the difference between hyperfine and super hyperfine. Don't forget it. Whether you are dealing with the organic molecule or you are dealing with the metal complexes. Okay. So, and then the parameters are more or less same. Your number of lines 2ni plus 1 into 2mi plus 1, so on and so forth. So there won't be much difference. Okay. So principle wise, you need not to be worried. This is how you should continue. Now, let us take few examples. Now, let us begin with the simple example. Now, we have taken one particular metal complex. Of course, metal complex cannot look like this. You have many other ligands over here. Okay, say, let us assume it is an octahedrally surrounded compound. That means there are 4 other ligands. Unfortunately, those ligands do not carry any nuclear spin. Hypothetical situation, they do not carry any nuclear spin, and they do not have your unpaired electron only. So our reactive site is only this portion, not that other portion. That's why you have not considered. Now this reactive site, and again hypothetically, that metal contains 1 unpaired electron. So S equal to half, Ms equal to plus minus half, and we have presumed that I of this metal is 0. Okay, so there is no nuclear spin as far as this metal is concerned, and it is connected to the hydride, 2 hydride, and each proton will have I equal to half, and they are equivalent. So as per our convention, so we have to consider 2 into 2 into half plus 1, so total 3 lines, right? And if you look at the splitting pattern is very simple, as we have already talked about, right? So this half, then this will be splitted with the, now here only one thing to remember, these two are equivalent, like your CH3 radical. These two are equivalent, so we need not to consider this plus this. Okay, if you consider this plus this, then that would be different, then it will be 4 lines, right? So you have to consider, like methyl radical, equivalent centers. So 2 into half, that means 1. So total I is equal to number of nuclei, equivalent nuclei, into the nuclear spin. So 2 into that way. So basically you are getting Mi equal to 1. Net Mi I am talking about. So net Mi means 1 means plus minus 1. So in between 0.